Okay, we're going to look at our next lesson, which is called the efficacy of scientific notation. And you might not have heard the word efficacy before, but it is a noun. That means the ability to produce a desired or intended result. So again, the results that we can get using scientific notation. All right, we're going to start off by watching a YouTube video on the powers of 10. And so we'll go ahead and watch this.
Picnic near the lakeside in Chicago is the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now every 10 seconds we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1 million meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1 million light years. Groups of galaxies bring a new level of structure to the scene. glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. 10 to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus, so massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Okay, so that was just kind of an idea as to what it means to be either 10 to a greater power or 10 to a lesser power, and this was way back in 1977, so you can imagine at this point we actually can see farther into the galaxy, and we can also see into smaller units, smaller angstroms, and get into the quarks of a electron or an atom. anyways, let's go ahead and start with exercise 1 and 2. Complete that on your worksheet. When you are finished, continue the video and get ready to take notes in your math journal. All right, this is what you should have. It was asking you to take, again, the mass of a proton and write it in scientific notation, and the mass of an electron. And again, write that in scientific notation. This is what you should have. All right, so let's go ahead and take this and do something with it as we continue to discuss why it's important to express numbers using scientific notation. Consider the mass of a proton, which we just did, and we wrote it in a more informative way, which is 1.672622 times 10 to the negative 27th power kilograms. Noting that the exponent negative 27 is used because the first non-zero digit, which is 1, right here. So if you're reading this number, the first non-zero digit we get to is 1. That number occurs at the 27th digit after the decimal point. So if you count from the decimal point to where the 1 is, that is 27 places. Similarly, the mass of the electron is much easier to read as 9.10938291 times 10 to the negative 31st power kilograms. For the same reason, the negative 31 is used because the first non-zero digit, if you're reading this number, is 9, and that occurs at the 31st place to the right of the decimal point. All right, so before we write the ratio that compares the mass of a proton to the mass of an electron, would you rather write the ratio in standard, which is decimal form, or scientific notation? Which way would you rather do that? And explain why scientific notation is more advantageous. So hopefully you said scientific notation. Why is that better to work with numbers in scientific notation rather than in those long decimal forms? So go ahead and answer that in your own words and then continue. All right, so let's take a look at exercise 3. Go ahead and complete that on your worksheet and continue. If you forgot how to take a word problem and write it as a ratio, you might want to research that first before you continue. All right, so you should have come up with this, writing a ratio that compares the mass of a proton to the mass of an electron, which means that you would write it either using a colon if you wrote it as a fraction, then the 1.672622 expression would be your numerator, and the 9.109 so on would be your denominator. All right, so let's take what we have here and use this for our example 1, which we're going to kind of spell out in our journal. So the advantage of the scientific notation becomes even more pronounced when we have to compute how many times heavier a proton is than an electron. So instead of writing the ratio R as this humongous ratio, which again it would be hard to keep track of how many zeros you have, it is better to express it in scientific notation. That way we can use the product formula to do our work on this ratio. So eliminating, which is better, eliminating the power of 10 in the numerator or denominator, and explain your reason for doing so. So as you look at that ratio, which power of 10 would you want to get rid of? Go ahead and answer that first before continuing. All right, well, if you use the theorem of equivalent fractions, we're going to eliminate the negative power of 10 in the numerator and denominator in order to see what we are doing. So anticipating that 10 to the negative 31st power times 10 to the positive 31st power is 1. That is by the property or the law of multiplicative inverse. We can multiply the numerator and denominator by the complex fraction, the complex fraction 10 to the 31st power. So it's going to look something like this. We're going to kind of cancel out the negative 31st by multiplying it by 10 to the 31st power, and this is going to give us 1. So that all we're left with is the decimal expression of the denominator. So using the first law of exponents, which is our 10th equation from our previous lesson in lesson 5, we're going to get, again, the canceling out, and from before, if you had negative 27 and a positive 31, that leaves you with a positive 4. So using that first law of exponents and subtracting, that's why we still have 10 to the 4th power here. And then using our product formula, remembering that in our order of operations, we can write this or rewrite it as the 2 decimal fraction parts times 10 to the 4th power. So now we're dealing with the decimal part and we're dealing with the exponents separately. So note that since we're using scientific notation, we can interpret the approximate value of the ratio right away. For example, we see that if we just deal with the decimal part, we can use some estimation and use our rounding. So 1.7 over 9.1, we can multiply that by 10 on both top and bottom to get 17 over 91. And again, using that information, we can estimate this as being roughly 1/5. And again, it depends on how you want to estimate it, but you would get somewhere in the vicinity of 1/5. You could have gotten a different common fraction, but as far as how they did it, they ended up with approximately 1/5. So that R is approximately 1/5 of 10,000. Now you might be asking where the 10,000 come from. Well, that's 10 to the 4th power, written out in standard notation. So 10 to the 4th power is 10,000. 1/5 of 10,000 is about 2,000. Thus, we expect a proton to be about 2,000 times heavier than an electron. All right, so for example 4, you're going to do the exact same thing, except you're going to look for a more precise answer to example 1. You're allowed to use your calculator to divide the decimal, and when you're finished, compare your approximate answer 2,000 to your more precise answer. And yours might end up a little different than what the answer is here, but we want something a little bit more precise than just 2,000. So go ahead and try your hand at it, and then continue the video. All right, so again, this is just one way of doing it, and one approximate answer. Again, it is an approximation, but we want to at least get it to a little bit more precise answer by dividing the actual numbers, or the actual decimals here, to get a different type of answer. Notice that as you read through this, again, yours might look completely different, but see if you can follow the logic behind each step. You might be asking, why did they go from decimals to whole numbers here? Again, it is to come up with, if you're dividing 2 whole numbers, you're going to get a different decimal expression. And again, this is just one way of doing it. But they came up with a more precise answer of 1,836, and again, yours might be slightly different from that. All right, so let's take a look at example 2, and we're going to do this on the lesson worksheet, and this time we're going to kind of walk through it a little bit ahead of time instead of having you complete it and then checking your answer. So here is our example, talking about the national debt, which is about 16 trillion, rounded to the nearest dollar, and comparing that to how many American citizens in 2012, which was about 313 million. So what is each citizen's approximate share of the debt? Again, we need to figure out, based on the problem, what type of operation are we doing? Well, this is going to be division, because we want to know how much money per person the debt is shared between. So how precise should we make our answer? Do we want to know the exact amount to the nearest dollar, or is a less precise answer acceptable? Make sure you go back up and read the question to help you answer that part of the question, this part of the question. All right, well, the most precise answer will use the exact numbers listed in the problem. The more numbers are rounded, the precision of the answer is going to decrease. So it's going to become more rounded. So as you round your answer, then the less precision is achieved. So we're going to aim for the most precise answer when necessary, but when the following problem does not require it, since we are finding the approximate share of the debt, we're going to go ahead and do some rounding. Now, this is just an example or a suggestion. They are deciding, or in this particular problem, they or we are deciding to round the debt to the nearest billion. We didn't have to choose that. We could have picked something else. Okay? So if we round to the nearest billion, then it becomes 1.6755 times 10 to the 13th power. Notice how all the rest of the numbers have been rounded, and this is our first billion spot. And then we've decided to round off the population to the nearest million. Okay, so just because we do billion for one doesn't mean we have to do billion for the other. So we're going to make this million, so that means this would be 314 million, or 3.14 times 10 to the 8th power. So again, you can choose, if you're going to be rounding, you can choose how precise you want to round it to. Okay, therefore, using the product formula and equation 13 from lesson 5, we see that each citizen's share of the debt in dollars is written like so. So here is the debt, here are the number of people, or the population, and again, using our product formula, we can split up the powers aside from the decimal portions. So what happens here is, because we can use our laws of exponents, 13 minus 8 becomes 5, so this is 10 to the 5th power, and then we haven't done anything with the decimal portion yet. So once again, we note the advantages of computing numbers expressed in scientific notation. Immediately we can approximate the answer, about half of 10 to the 5th power, or $100,000, which is about $50,000, because, and we're going to go back to this part right here, that 1.6755 over 3.14 is approximately 1.7 over 3.1, which, if we turn them into whole numbers, is 17 over 31, and 17 over 31 is approximately 1/2. So that's why we're saying half of 10 to the 5th power, because this would be 1/2 times 10 to the 5th power. And 10 to the 5th power is 100,000, so half of 100,000 would be 50,000. So more precisely, with the help of a calculator, let's go ahead and take our decimal fraction here. And again, they've chosen to write them as two whole numbers and then divide them. Again, since you're using a calculator, you can just type it in, but this is the number you will get, which we can round to this particular number. When you do that, because you're going to multiply that by 10,000, that's going to move your decimal point 5 places, which is where you get 53,360. All right, so it's your turn. Go ahead and do exercises 5 and 6 on your worksheet. Check your answers when you are finished. Again, you're going to be doing the similar thing, and your answer might not come out precisely depending on how you round, but at least when you check your answers, see if your level of logic and going from step to step is the same. All right, so you should be done with 5 and 6 now. Let's go ahead and check your answers. Make sure that you can see how each one of these is matching up with the numbers in the problem and how they went about showing each step of the problem. And again, if yours is not exactly like this, that's okay, but you need to have at least a similar level of detail. Again, if you have any questions, write them down, highlight them, and make sure you bring them to class. All right, so to wrap this up, you should be able to summarize this lesson in your own words, be able to explain this to another student in case you're asked to help. and that we can read, write, and operate with numbers expressed in scientific notation. All right, we'll see you in class.